Okay, so I'm gonna today talk about the conservation of momentum, which is applied to a particular control volume that we would select. Okay, all right. The first equation that we're gonna write down is gonna be the Newton's second law. Okay, so basically what it says is the rate of change of linear momentum is equal to the summation of forces. Okay, as you note right now that this is a vector equation, not a scalar equation. As you know, the scalar equations do not have direction. Vector equations have directions, so they will have components in the directions that you're interested in, such as x, y, z, or r, theta, z in the polar coordinates. Okay, so basically this is Newton's second law. Now I'm going to actually insert what linear momentum is. And you may remember from your physics courses that linear momentum is equal to mass times the velocity. Okay? So this formula then becomes summation of the forces becomes d dt. Remember, this is a material derivative because this is applied to a particular point in the flow. Okay? And v. Alright. Next is I'm going to remind you the Reynolds transport theorem and see whether we can play with that. Okay? So dB dt, b was just a placeholder, del t of triple integral over the control volume b, lowercase b, the volume, plus control surface b rho velocity dotted with n dA. Right? This was my Reynolds transport theorem, and I can apply this to conservation of mass, momentum, energy by replacing this b value in here. Okay? Alright, so what I want to accomplish today is I'm going to be strategic and insert this capital B is equal to this MV. Okay, because if you take a look at it, if I simply go ahead and insert this right over here, what will happen is on the left hand side of the equation is I'm gonna get d dt of m times v, which is the linear momentum, and I'm gonna go and say that this is equal to sum of the forces. That will be giving me something useful for me to work with. Okay, so let me repeat what I said. This capital B is equal to m times velocity vector, and if you remember from our earlier discussions, the ratio between the capital B and lowercase b is per unit mass. Okay, and I'm going to insert here m velocity vector, and from here I'll get the lowercase b as velocity vector, right? You can see m's will cancel out. Okay, all right, so now I seem to know everything that I need to proceed. Okay, so I'm going to say that d mv dt, which is the linear momentum, I'm going to use Newton's second law and say that this is going to be equal to the summation of the forces. Now, and then I'm going to write the right hand side of the equation. So it's going to be del t, and again triple control volume rho velocity vector d volume. Be careful about these symbols, they look close to each other, right? And control surface rho velocity vector velocity dotted with n dA. Okay, so then actually I'm going to go ahead and box this equation up, as this is my main equation for the conservation of momentum. What I would like you to note that this is a vector equation, as I mentioned before, and it will have components in the x direction, y direction, and z directions. So now I want to go ahead and write these three equations if I'm using the Cartesian coordinates, okay, for your notes, for completeness purposes. So the summation of the forces in the x direction will be equal to del t triple integral over the control volume rho vx d volume plus over the control surface rho vx v dotted with n dA. Okay, you can have the similar equation in the y direction as well. So you'll get del t of the control volume rho vy d volume plus over the control surface rho vy v dotted with n dA, and the third one will be summation of the forces in the z direction will be equal to del t 1, 2, 3 control volume rho vz d volume plus over the control surface rho vz v dotted with n dA. Okay? Okay, now I have the three components that I need. If I go up here, as I mentioned, this is a vector equation. When we look at the conservation of mass, we have seen that that is a scalar equation. And typically what happens is, that is the left-hand side was 0, okay, is equal to, let's say, the first term is plus 5, the second term has to be minus 5. As simple as that, okay? In here, it's a bit more complicated, okay? The left-hand side is the summation of the forces. So if you think about it, this is still the Newton's second law, okay? So this is the fluid's equivalence of F is equal to ma. The right hand side is ma, actually, if you think about it, okay? Let's say that this is vector 1, this is vector 2, this is vector 3. What happens is, let's say that vector 2 is like this, okay? And let's say that vector 3 is this, right? And then this is what it means. This 1, or the summation of the forces, will be the summation of the vector 2 plus the summation of the vector 3, okay? So this is quite different than the conservation of mass. I would like you to realize that. Okay? Okay, let's talk about the special cases of linear momentum. The first thing I want to highlight here is the first assumption or special case that we have evaluated when we're doing the conservation of mass was the steady flow. And I will do the same. Okay? What did steady flow mean as another recommendation? Did it mean that the velocity is constant throughout the flow? No, it doesn't. Okay? And I gave the example, I was doing an experiment in my lab and I take a break, I go to the lunch, I come back from the lunch and nothing has changed, okay, in terms of the fluid's flow characteristics wise and properties wise. So that means that the rate of change of things over time will be 0, okay? Steady means that, okay? And if I go up in here, if I look, let's say, look at the z equation, you will see that the first term is looking at how does this triple integral changes over time. For a steady case, the answer would be it doesn't change, okay? Because del of del t of this triple integral over the control volume velocity vector times rho times d volume will be equal to 0. I'm talking about more this equation, okay? So you can see that I numbered it as number 2 vector, turns out to be 0, okay? And what it basically means then, my summation of the forces will be just this last term. So it will be over the control surface rho velocity vector, velocity dotted with n dA. So this will be the equation that I obtain after I go through this process, okay? And I gave the example of vector 1, vector 3. If I use the same analogy, so what it says is vector 3 and vector 1 is identical. So if 1 is 3, 1 is 1, because 2 is 0, right? So the vector 1 and vector 3 are the same. That's what it means. So when I was doing the conservation of mass, you may remember that I did steady plus incompressible flow, right? So I don't really need to do it in here, because in that case there was a density was able to take out of the integrals. Left hand side was 0, so I divided everything by the density, so I cancelled out the density. I don't have anything like this in here. Maximum what I'm going to obtain, if you're looking at this box type equation, is if the density is out, it's going to be summation of the forces divided by density. It's not that special, okay? So then I'm going to go ahead and make my second assumption as steady, and I'm going to add one more to it, which is called the uniform flow, okay? So also I see some confusion for the definition of uniform flow, so let's discuss that for a minute here. Uniform flow does not mean that the velocity is constant, okay? The uniform flow means that I have, let's say that I have this shape, right? In an example, one inlet, two outlets, okay? Remember, vectors are defined at a point, not at an area, okay? When I say velocity at the inlet is equal to 5 meters per second, then I need to be much more specific and say at the inlet at this particular point the velocity is 5. This uniform flow assumption will enable me to say that, hey, the velocity at the inlet, regardless of which particular point that I take, is the same. It doesn't change. Okay. However, it doesn't say that this velocity will be equal to this velocity. All right. So now, if I go ahead and with this steady and uniform flow assumption, what I'm going to have is the equation will be the summation over the exits. What it will enable me to do, you can look at the video from the conservation of mass how I obtain the summation sign. Because integrals, as you know by definition, are we take small areas and we add them up. So I'm kind of going back to the definition of the integral, okay? Rho exit, v exit, vn exit, a exit, okay? And I'll talk about this vn exit in a moment. Summation over the inlets, rho inlet, v inlet, vn inlet, a inlet, okay? Now, let's look at this n terms. This what I mean by Vn is, I'm going to underline here as well up there in the box equation. That is what I mean by Vn. So this is the velocity at the inlet. Okay, the velocity at the inlet and velocity at the exit. But it doesn't have any components in the x, y, z. It's in the normal direction. Okay, at the exits, if you think about it, let's say this exit, you can see that the normals, if I'm drawing the normals over here in the figure, you can see that they are aligned with the velocity. So that's why I'm going to get a positive sign in front of the summation. At the inlets, if you think about the normal is pointing away from the surface, right? But the velocity is to the into, so I'm going to get a negative sign. That's why this negative is. And so I would like you to be careful, and although this is not an official way of representing this, I'd like you to think that there is no negative sign associated with either Vn inlet or Vn exit. Granted, I do know that inlet is a negative, that's why I have the circled up negative sign over there, okay? So now, we talked about this as well, so I'm gonna actually take these three terms and see what these multiplication of these three terms are. Rho V A, okay? The multiplication of V times A, if you remember, V times A was the volumetric flow rate, and if I have V times A times density, that will be giving me the mass flow rate, okay? So I can simplify this equation further. It's not even simplification, it's just for mathematical purposes. I'm going to have my exits as m dot exit times v exit minus over the inlets m dot inlet vi. Okay, so this is another version of this particular formula as well. The last thing I want to talk about is the left hand side of the equation. I didn't really need to talk about the left-hand side of the equation, any of these assumptions, not particular to assumption number 2 or special case number 2, but any cases. I have to look at the forces, okay? And from our experience, what we noticed is there are three common types of forces that we have to account for in all of the cases, or we have an assumption for stating that this type of force doesn't exist, okay? And those three types of forces are, first one, it's going to be the surface forces, and typical one is the pressure force. Okay, if you think about it, the pressure force is P times A. So I need to know my pressure value. If I multiply by area, I'm going to get a force. So I have to account for it. Okay, and I want to talk about it in here because I see issues here as well. So let me write this particular example again, or rather draw again. I have an inlet here, I have an exit here, and I have an exit over here, okay? As we discussed in the fluid statics section as well, pressure always pushes it in. If I have a balloon like this, any particular shape, it always is perpendicular to the surface and pushes it in. So when I pick my control volume in a traditional way like that, what will happen is I have to indicate the direction of the pressures to be pushing into the surface. So if I draw with longer arrows, so this is going to be the P1A1, if assuming this is section 1, and careful, this is P2A2 pointing it in, and this is P3A3 pointing in as well, assuming this is section number 3, this is section number 2, and this is section number 1. If I change the direction of the flow, let's say that 2 and 3 becomes an inlet and 3 becomes an exit, what happens to the direction of the pressure forces? Nothing. It still stays the same. Note that the direction of the pressure forces has nothing to do with the direction of the flow. I see these issues often from the students that didn't quite understand the topic well. Okay? The second force are viscous forces. Okay, viscous forces are similar to friction in your solid mechanics courses. Okay, when I have a pipe, the flow is flowing in it, there will be some kind of a drag on it, right? It's going to slow down. If I don't have a pump, you just turn off the pump, what will happen is the flow is going to stop, right? That is the force stopping the flow in my pipe. Okay, it's called the viscous forces, and we touched upon this in the first introductory concepts videos. So it's going to be the viscosity times du dy, remember that? And if I multiply this by area, I'm going to get myself viscous force that I should be incorporating to my analysis. And this viscous force will be opposite to the direction of the flow. So now this one has something to do with the direction of the flow. Okay. If you want to get rid of this particular force because you weren't given enough information, then I can just simply say this is inviscid flow. Okay. Inviscid flow means that this is zero. So then I don't have to worry about viscous forces. Okay. And the third one is, I want to call it body forces, but the most common one that we know of is the weight of the control volume. Okay, the weight of the control volume. There's also magnetic forces sometimes that act on my flow. That's a body force, but that's not as common as the weight.